Somebody asked me about, what was it, number, I think it was number 5. We did something like number 6 in class, right? I think we did 5 and 6, didn't we? No.
I don't know, I have
6.
a question about number 7.
We did 5.
7, yeah. Somebody emailed me about 7, and I posted it to the forum. So if you go to the forum, you'll see there's a new message there from me with my explanation. So I'm going to do this one right now. Somebody said, yeah, they got it in class number.
There's a question about number 6.
Maybe that's what it was.
Oh, that was the one that didn't have a question on it.
Yes. Oh, yeah. Okay, so thank you for reminding me about that. Okay, let's see. Can I get that from here? So in the forum, if you post a question, whether it's anonymous or not, you got to have a question. You can't just put something up there with no question and say, this is the problem down there. So I wrote, what's the question here? That is, what's the problem you're having? So you got to state, you can't just say, I didn't get it. You got to ask something specific about the question and maybe state what you tried. Okay, so if in the future somebody posts something like this with just the problem from the homework with nothing to go with it, I'm just going to delete it until somebody posts a reasonable question about the homework problem. Okay.
Yeah, I have a question on number 4.
Okay. All right, let's take a look at a few of these and then we'll move on. So we've got this, and we're just going to let epsilon be epsilon, and we need to figure out what delta is. So let's do it. Before I do that, I'm just going to state the precise definition of the limits. Oh, did anyone see that I posted a printable practice test? Anyone saw it? No. It's there. Check it out. It's way too long. Right, I couldn't I got to resync my board. Something went wrong. All right, that means I get to straighten it out because the angle is bugging me. That's better. Just work too fast here. So check out that sample test. There is a whole bunch of review problems, 40 something, and now there's about 30 problems in a printable version of the test. You can go there, print it out, or just look at it on your screen, your call. So precise definition of the limit. So if you have a limit, so the limit as x goes to a of some f of x, and the limit is some real number L. So this doesn't count for infinity. Infinity isn't a number, it's a direction. You gotta have you gotta hit a number, so L is some number. So what it says is for all numbers epsilon that are greater than 0, and epsilon is supposed to be a little number, that's the dare, how close can you get to the function? There exists a little tiny number called delta that's also greater than 0, but a little tiny. Such that if the distance between f of x, any y value, and the limit, if that's less than epsilon, right, within that's kind of our margin of error, then x minus a, we can find an x value that's close enough. Right. So the way it goes is I say I need you to be this close to the final answer, that's our epsilon. You say get this close to x and you'll be okay in the end. You're close enough to the limit, those x values. So that's the statement. Let's apply it to this problem. So new page, screenshots. Screenshot, there you go, right there. Oops, I cut off part of it. We can read it enough. Let's try that again. Screenshots. There, okay. So we build it pretty much the way that second line is stated. We state the function part inequality first. So that would be the absolute value of f of x minus L is less than epsilon. And remember our goal, sure, let's do purple. Our goal is to make that look like x minus a is less than delta. And so it's a discovery. What could delta be for that to work? And sometimes that discovery is not too bad, sometimes it is nasty. I mean challenging. So my f of x here is 1/3 x minus 3. Then I subtract my limit, so I'm subtracting a negative number, which is going to be a plus 16/3. So we get some fun with fractions. So this is our starting point. We're not given that epsilon is like 0.1 or 0.01. We're just stuck with calling it epsilon for now. Now we have a -7 there. So we need to make this look like x minus -7 or x plus 7 is going to be our goal to make it look like. All right, because of that part right there. So we got to morph this thing into that thing somehow. Right. Suggestions. Can get rid of the fractions.
Yeah.
Multiply everything by 3, because 3 is the denominator. So if we do that, we're going to get, and remember there's two approaches. We can get rid of the absolute value by making it a compound inequality, or we could leave it as an absolute value. I'm going to leave it as an absolute value. Remember that was a little less work yesterday? So that's going to give me, if I multiply by 3, I'll get x minus 9 plus 16 is less than 3 epsilon. Whoa, it's kind of like mirror images. Cute. And -9 plus 16 is 7. Oh my gosh, we're done. That's the goal, isn't it? We were trying to get it to look like absolute value of x plus 7. What's on the other side of the inequality? 3 epsilon. So let's let that be our delta. And that's it. The question said let delta be a function of epsilon. That's a function of epsilon. Take 3 times epsilon and you're okay. Yeah, so that should be the answer there. So, we could double check that by plugging it into that Desmos app that was linked in problem 6, I think it was. So I just bring that up, see if we can make it work. Visualization. All right, so what do we got? 1/3 x minus 3. And then a is -7 here. Ah, this one doesn't work for negative numbers, I don't think. Or at least the picture falls apart. Let's see if we can get it to work. That ends up being off the screen, down here. Maybe it'll work. Okay, so we lost the vertical bars, but we can still play with delta and epsilon. So what did we say? Delta had to be 3 times epsilon?
Yeah.
So let's suppose epsilon was 0.1, then delta would be 0.3. Does that work? Does that give me the right epsilon here? Yeah, epsilon is 0.1, delta is 0.3. It looks like it works out. If I said epsilon was 0.01, what should delta be? 3 times that, or 0.03? Yeah, it looks like we found a reasonable match there. Okay. So answer is 3 epsilon. Whew, got it right. Okay. So you'll have slightly different parameters, but clear the fractions. It works out pretty well once you clear the fractions. Okay, other question was on number 6. And number 6 is different every time. Sometimes it's going to be linear, sometimes it's quadratic, sometimes it's something else. I think the one somebody asked in a homework looked a lot like this one here. What's up?
Okay, it's about number 4 again. So is there a pattern to it? Would it always be the denominator?
There is a pattern. Yes. It's related to the slope. Yeah. We did a linear function in class the other day. I think it was something like 2x blah, blah, blah. And epsilon ended up being, delta ended up being epsilon over 2. This time we had 1/3 x, and delta ended up being 3 times epsilon. There's definitely a pattern linking the slope of a linear function and the relationship between delta and epsilon.
So you don't need to know how to do math, just got a pattern, right?
What's that?
So you don't need to know how to do math, just find a pattern.
That pattern only works if it's a straight line. After that, it's just a pain in the butt. All right, so let's do this one right here. This is almost the same problem, except it's a little easier because they tell us the value of epsilon. So we'll do it again. And then we'll do the wicked hard problem.
Number 7.
Yep. I just need that part right there. All right. So remember how these work. We do the f of x part and try to morph it into the other part. So we're going to start off with f of x, 3x minus 1, minus the limit. Let's see, if I plug 1 into that, what do I get? 2?
Yeah.
So the limit there is 2, so minus 2. So that's f of x minus L. That has to be less than epsilon, which is 0.05. My goal is to make this look like what? Absolute value of,
X minus 2.
not x minus 2, x minus 1. Yeah, whatever x value we're heading to. So my goal is to make it look like that. And there's a couple ways to go about doing this. Yeah, William?
Where'd you get the 2?
I plugged the 1 into my function. Right, because I'm trying to find what's the limit as x approaches 1. Since this is a linear function, I can just plug it in according to the limit laws. So the limit here is 2. So I will fill in a little piece there. Let's shift this sucker down a touch. So again, what I'm trying to justify here is that the limit as x approaches 1 of 3x minus 1 is 2. And someone says, okay, I need you to tell me what x
Where'd you
values.
get that 2 from?
What's 3 times 1?
Oh, it's 2.
Minus
Oh,
1?
yeah, okay.
2, okay.
Okay.
So they didn't give me the limit, I had to calculate it here.
Okay.
All right, so let's see, let's clean this up. Like terms there, so this becomes 3x minus 3. And divide everything by 3, yeah. Come on, there we go. Divide by 3, divide by 3. 3 goes into 3x, leaving an x. 3 goes into negative 3, leaves a minus 1. And on the other side, I get whatever that is, 0.05 over 3. So this is what delta should be. Let's see what kind of answer they want. I think they just want a decimal approximation. Click, enter an integer or decimal number. Yeah, so then I just whip out my calculator. What is 0.05 over 3? 0.016666. If I'm not told how to round it, usually I go like 4 or 5 decimal places. So then for this one, I'd probably go 0.01667. Is that 5 places? That should be good enough. I got it. What if I tried to go 3 decimal places? Ooh, doesn't mind that too. 2 decimal places. Oops. Oh, been like that. And it says, it should have been more like that. All right, next. This one's a beast. So I mentioned if you really dig this stuff, then you're destined to be a math major. If not, I'm not sure what your destiny is. Could be lots of different things. Could be a math major, but maybe something else. Here, we're given a much more complicated idea about what delta could be for the given function. And if it's a linear function, the limits aren't following the precise definition isn't that bad, right? Those 2 problems we did, they weren't too bad. I know when you went to do them on your own later, they're like, what? Because it's a crazy definition, it's complicated. Any other function, it's really hard to do. So if you just randomly pick some function and say, show me what the limit is with the precise definition, I will struggle mightily to come up with an answer. This is not an easy thing to do for anybody. I assigned this problem because when I was looking for cute homework problems for you guys, it took me 3 tries before I get this one right. So I'm like, all right, let's see what the class can do. Because generally what I find when I teach this class, most of the students I have are smarter than me. I just happen to know more math. So this is just my test to you guys. It was a hard problem. All right, let's do it. And so every once in a while, I will assign a pretty tough problem for you guys to struggle with. All right, so we've got this limit, we got this function. So I'm just going to summarize a couple things and play around and figure out what I should do. So my function, f of x, is x squared plus x, okay? That value for x goes to a, right? That's 1. And f of 1 is 2. So the limit tells me all of that information right there. I'm given that epsilon is just some number. I don't know what number, just some small number. And here they're saying, okay, you get to pick delta to be either epsilon over m or to be 1. Okay.
What do you use minimum?
Minimum. So that means delta is the minimum of those two things. So delta is the minimum of epsilon over 2 over m. Oops, I put 2 in there. Pretty sure it's not a 2 or 1. Now, we did other problems where we ended up with the answers like epsilon over 2 or 3 times epsilon. So that happens sometimes. 1, man, I like that. Sometimes we ended up with answers like 0.01666, but there's no reason delta couldn't be 1. Usually we want it to be smaller. So, okay, what if delta was 1? I'm going to go with the easier part. Doesn't that sound like easier than choosing epsilon over m? Sure. Because epsilon's a variable, m's a variable. That's a lot of variables. Now I'm going to take the easier route to start with. Fine. Let delta equal 1. So where does that fit in? Well, that's the last part of the precise definition. It says that x minus whatever x value you're targeting has to be less than delta. We're saying delta is 1. What does that mean for x? What x values fit that description? So remember the intuitive definition of this whole statement right here? There's 2 ways to view it. One is the distance between x and 1 has to be smaller than 1. Okay. Do I know what x is? No, but x is some number that's no more than 1 away from 1. Make a number line with 1 in the middle. Which one is that? That's that one right there. This is the most I can be away from 1. Okay, so how far to the right could I go?
2.
Up to 2. How far to the left could I go?
0.
0. So x has to be some number between 0 and 2 if delta is equal to 1. That's what that tells me. It says don't go any farther away than that, otherwise you're too far away. And so that's the interpretation of that limit right there. So I've nailed part of this. I've got that part done. Now I got to play with the other part, the epsilon over m part. So for that part, I am going to do what? I'm going to go the other direction. Instead of starting with x minus 1 is less than epsilon over m, I'm going to go to the way we usually start these. So my function is x squared plus x. My limit is 2, so then minus 2. That has to be less than some epsilon. And I'm going to change colors because that looks like I'm angry. There we go. It's better. All right, so somehow I have to make this look like x minus 1 is less than something. Okay, that's the hard part.
Why don't we just factor it?
Oh, let's factor it. That's a beautiful idea. So this factors as, oh my gosh, x minus 1 times x plus 2. That's cool. I'm now partway toward my goal. I see an x minus 1 inside there. Now, it would be great if that x plus 2 was gone. With me?
Yeah.
Okay, so that's where the previous part helps me out. What's the biggest x could be here, given this information?
2.
2. What's the smallest x can be?
0.
0, okay? I'm gonna say, let's err on the high side, let's just let x be 2 here. Now, I'm only saying that for this part right here, because I'd like that to go away. Okay. Because what happens if I try to get rid of that here?
It just ends up with epsilon.
I can put it on the other side, but the problem is it's inside an absolute value right now, which means the absolute value is forcing that to be positive. But let's think about that for a minute. When is this going to be negative? Well, only if x is like -3 or -4 or something like that, right? What values of x does this part say I'm working with?
Positive values.
Positive values for x. So can I divide by x plus 2 if I'm just working with positive values of x?
Yeah.
Yeah, it's not negative at this point. So I'm just going to make a little note. Since x is greater than 0, x plus 2 is also greater than 0, which means I can pull it out of the absolute value without damaging stuff. Also, it's not going to be 0, so I can divide by it. Agreed? The only time it's going to be 0 is if x is -2. We ain't anywhere near x equals -2. So I'm just going to divide it. So that gives me that the x minus 1 there is going to be less than epsilon over x plus 2. And then I'm just going to go with like the worst case scenario. The biggest x can be, according to the other page, was 2. So if x was 2, according to the other page, then this right here is just epsilon over 2 plus 2, or epsilon over 4. So that's a possible value for
So
epsilon.
then how do we determine m? Because that's what's m plus.
I have a number in the bottom now, right?
Well,
Let's
yeah,
let m equal 4 then, based on the previous page.
but m could also equal 2.
M could be 2. Yeah, there's a lot of different things m could be.
So how do we get the right answer for the question? Because if m could equal anything from 0 to 2,
No, m, if I'm stuck in this inequality right here,
yeah,
x could be anything from 0 to 2.
okay.
So in here, that means m could be, like if that was a 0 instead, m could be something from 0,
From 2 to
2
4.
to 4. 2 to 4. So I'm just going to go,
It's still a
let's-
lot of numbers.
yeah, well, that's okay, let's pick one. Which one should we pick? I'm recommending 4. See what happens.
Sure, why not?
And this is the bottom line. If the function is linear, it's pretty straightforward how to pick delta given epsilon. If the function is not linear, it's not straightforward. And I'll show you a picture of why in just a sec. So I'm going to say, hey, let's try m equals 4. Ooh, I like that. Let's try m equals 3. Is it like that one? Oh, I didn't like that one. Okay, so we're going to go with 4, the extreme case on the right. That one worked okay.
Still answering.
If except 2.
I don't think so. Oh, I lost the submit. Is it going to change it on me? Ah, it gave me a 30 over there and a 5. All right, I'm not redoing it. It's the same process, though. Give it a try. So I wrote all those steps down in the forum with my own post right here. So the same things we just did. And
So
I
we just have
typed
to
their
guess on m or just use the high end m?
Use the high end.
Use the high end.
Yeah, just use the high end.
Okay.
Yeah.
It's 3.
All right, we are moving on. In terms of the importance of stuff we've done so far, limits are important. Continuity is important. Precise definition is only important if you plan to be a math major in the future. Otherwise, you just need to get through next week. So chill out.
So I can get through next week and then totally like
Totally forget about it.
forget all of this.
Yeah,
Cool.
totally. All right, so anyway, there's a link to the printable sample exam there. It's got almost 30 questions. That's way too long. It's probably 3 times too long. You're going to end up somewhere between 10 and 15 questions to answer. The review has 40-something questions. Don't say just.
No,
I could ask one
no.
question that would keep you busy the whole time, so be careful. All right, chapter 3. We're finally into like the big question of calculus, which we actually already started in section 2.1, defining the derivative.
This is where I got lost.
Okay.
Last 2 times I took this class.
Okay, well, not this time.
Okay.
So, all right, so this is all of chapter 3 is on the derivative of the function. And there's just a ton of things that we can do with it because there's a ton of different kinds of functions out there. The derivative of the function calculates instantaneous rate of change. We can also look at it as slope of a tangent line to a point on a curve. Let us do a quick review of slope and lines, and then we'll jump into calculating a derivative. So suppose that's my function. To find slope, you need 2 points. So if I go from there through there, I can find the line, right? So the question is, well, how do you find a line if you have only 1 point? Well, it turns out you have 1 point and a little extra information, because anywhere you are on a curve, like maybe that point right there, if you are standing there, you're standing on a particular angle, right? So the question is, how do we find that angle? Slope is one way to measure an angle. So it turns out you can measure an angle at a particular instant. It's just a little tricky. So this red line is called what kind of line? Anybody remember? Secant. That's called the secant line. We want to turn that into a tangent line, and so the trick there is, let's make a copy of this sucker. Go. Change my color, sorry about that. There we go. So now I have just a single point. So let's say it's that same point as that one right there. I need to figure out what line matches. Ooh, that's not a line. Make believe it's a line. It's straight enough today. I want to find that line right there. That's the tangent line. Tangent. Now, near this point, that line only touches at that point only. Now, if the curve doubles back, like it loops like it has some kind of max and comes back down, it's going to hit that line again. But I'm only concerned about that region right there, very close to that point. Okay. So we need to learn how to morph a secant line into a tangent line. Slope is the key. Slope. Rise over run. Rise is your change in y values divided by your change in x values. How do you find that change? Well, it's a subtraction. You've got 2 points. There's a y value on the second point, subtract the y value from the first point. If you started with the second y value, you better start down here with the second x value and then subtract the first one. Right? That's our slope formula given 2 points. No big whoop. That makes the secant problem not a big deal. We, however, use function notation. So if I say y is equal to some function of x, then I can rewrite the slope formula in function notation. F of x2 is how I would have calculated the y2, right? Plug in that x value. F of x1 is how we calculate y1. Divide by x2 minus x1. So that's the function version of slope between 2 points. Right? Slope of a secant line. To turn it into a tangent line, I need these 2 x values to merge together. Right? So what I would want to do for this thing right here is I would want to be able to take the limit of it as, let's say, x2 heads toward x1. Okay. So let's say x1 is my target point. I want the slope at that point. So I just move point x2 on top of x1 and see what happens. Okay. Now, if you just try to cheat and do that, you get 0 over 0, which could be anything. Could be defined, could be undefined. We don't know. Right? So we have to use some trickery to make that happen. Picture of this. Back to that curve I had a minute ago. Is there we go. So let's say right down here is my x1, and right down here is my x2. So there's the x-axis. Y-axis is over here somewhere, so this would be my y1 or f of x1. Up here is my f of x2. So a slightly different way of looking at it would be to say, find that distance and call it h. Yeah. Then x2 instead can be written as x1 plus h. Now, since I don't have 2 different x values, I don't need to call them x1 and x2 anymore. So what we usually do is we just call the first one x, and the second one becomes just x plus h. We can ditch the subscript at that point. Okay. But the slope is the same thing. Same thing. I need to calculate my rise. Well, this would just be f of x there. This one would be f of, what's my new x value?
X plus h.
X plus h. To find that vertical distance, I just take f of x plus h, and I subtract f of x. Right, that's my rise. My run is just h. Yeah, so that's the alternative version of the slope formula. M equals f of x plus h minus f of x all over h. Slope of the secant line. If we let h get smaller and smaller and smaller, we turn it into a tangent. Turns out, some days this formula is easier to work with than this formula. But other days, this one's easier to work with. It depends on the function. So I'm going to do a couple problems to your this here. So we're going to see this a lot over the next 2 weeks. Once more on the final exam, and then you'll probably never see it again.
Oh.
All right, so let's just pick a function and a point. F of x equals, how about 3x squared? The point of interest here, let's let that be 2. So we need to know the y value. So y would be f of 2. That's 3 times 2 squared, which is 12. Okay. So I'm trying to find the point, the slope on this curve at 212. So quick sketch of this thing. In that vicinity, I'm going over to 2. And then I have to go up at least to 12. So let's say we go 1, 2 that way, 5, 10, 15. I'm just going to rough it out. Let's make it black. So we definitely have the point 0, 0, right? And then we're going to have the point 1, 3, which is going to be somewhere over here-ish. And then we'll have the point 2, 12, which is somewhere over there-ish. And then let's see, 3 would go with what? 3, 27. Oh shit, that's way off my chart. 15, 20, 25, 30. That's not too bad. If we decided to go all the way over to 3, then y would be 27, which is somewhere up. Let's see, 15, 20, 20, 30. Right about here. So here's that part of that curve. I need to know what's the slope right there. Now we can do secant approximations like we did before and look for the pattern. We're just going to jump straight to the limit version of this. Here's the way I recommend you approach this. If I'm going to use that formula I had a minute ago on the board, that the slope of the tangent is going to be equal to the limit as h, goes to 0, f of x plus h minus f of x all over h. I don't know about you guys, but when I first saw that, it was very daunting. You know, that would be like, looking at that was like somebody telling me to climb this 50-foot cliff without a rope. It's like, oh my gosh, that looks so dangerous. Okay, so here's the recommended order of operations on this thing. Step 1, find f of x plus h. Just break it down. All right, I can do that. That means wherever there was an x, throw in a parentheses. And inside that parentheses, I'm going to put what? An x plus h. All right. This is one of the tricky parts. To square something means multiply it by itself. So that means this is really 3 times x plus h times x plus h. There's no shortcut for squaring something. So holding the 3 aside for a minute, that's going to give me an x squared plus an xh plus another xh plus an h squared. So altogether, in the middle, I have 2 xh's, okay, and then I got to multiply everything by 3. So this part right here, I get 3x squared, 3 times 2 is 6 xh's plus 3 h squareds. Some of the videos I posted to go with this by another teacher, they do this entire thing in one shot, the red thing in one shot. Certainly you can try it that way, but it's not my recommendation. So step 2 here would be to do the subtraction next, right? We did this part, now we're going to move over to the subtraction, so I got to figure out what is f of x plus h minus f of x. Well, I already have the f of x plus h, right? All I have to do is subtract from it the original function. So that means I have my 3x squared plus 6xh plus 3h and h squared. And what am I subtracting? The original function is 3x squared. Hey, that's wonderful. Look at that. The 3x squared is now going to go away. That cleans up a little bit. That gives me a 6xh plus 3, oops, I missed the 3, 3h squared. Guess what we're going to do next? I missed my 3 again. Here's a 3 there, believe it or not. Okay, we're just going to divide by h would be the next part. That would be step 3. A new page because I'm on a room. Step 3, take that f of x plus h minus f of x. We found that to be 6xh plus 3h squared. Is that right? Yes. Mm-hmm. And we need to just divide that by h. So some h's cancel, right? So h goes into 6xh, leaving a 6x. But h also has to go into 3h squared, leaving a 3h. Getting there. What's the last step? Take the limit. So step 4 is to take the limit as h goes to 0 of whatever that fraction ended up being. Well, we found that fraction is 6x plus 3h. What happens to that if we let h go to 0?
It becomes 6x.
6x. Okay, what x value was I concerned about here?
2.
I was concerned about 2, so if x equals 2, this says here that the slope of the tangent line should be 6 times 2, or 12. Let's test that on a graphing thingy. So how do you graph a line through a point? Do you remember the point slope form of a line? Y minus y1 equals m parentheses x minus x1. You can just plug that into Desmos just like that. So here, what's the point of interest?
212.
212. So I'm going to have y minus 12 equals, what's my slope? That's also 12, coincidentally. That's just a coincidence. And then x minus 2. So I'm going to graph that along with my original function and see if it looks tangent. Here. Okay, so my original one was f of x equals 3x squared. Oops, squared. I want to be able to see the point 2 comma f of 2. Now I could have just typed 212, but I just want to make sure, you know, I didn't make a mistake. And yep, there's 212. And now I want y minus 12 equals 12 times parentheses x minus 2. Ooh, doesn't that look good? Zoom in there to kind of take a peek. Does it look like they match up? Yeah, the scale's kind of freaky, but they do. So you could go monkey with the scale. So to do that, I could go here. Let's see, x, I just want to be close to 2. So how about 1.5 over 2, 2.5 maybe. And let's see what that looks like. Yeah, that looks pretty darn tangent, doesn't it, to the curve? Yeah, and again, depending on the slope of the curve, if the curve is shallowly sloped, they're gonna like sit almost on top of each other. It's gonna be hard to distinguish them. All right, I think we did it. All right, let's try another one. I'm gonna do this one a little different, pick a different function. Let's let f of x equal 1 over x. And let's say the x value I want to play with is 2. So the y value would be f of 2, which is just 1/2. So the point of interest is at 2 1/2. I want to find the slope there. So I'm actually going to do it in a slightly different way last time. I'm trying to find the tangent, which is the limit as h goes to 0. Instead of using f of x, I'm going to plug in the x value I'm interested in instead of x. So I'm going to say it's 2 plus h minus f of 2 divided by h. So that's what we're going to go over here. Where do they get the 2 from? Right there. Okay, so step 1, just like before. This is step 1 right there. What is f of 2 plus h? Well, that would be just 1 over 2 plus h. Nothing really to do with that. Done. Move on. Step 2. What happens if I take that thing and subtract f of 2? All right, well, that would be a 1 over 2 plus h minus 1 over 2. I should do something to this. Make it a single fraction. 2 plus h doesn't factor, so the denominator is going to be 2 plus h times 2. That means the first fraction, I'm going to have to multiply top and bottom by 2 to get the common denominator. And the second fraction, I'm going to multiply by 2 plus h. So I'm going to multiply by 2 plus h here and 2 plus h here. Okay, so my numerator then is now 2 times 1 is 2 minus 1 times 2 plus h. And I'm slowing down here to get the algebra right. What do I have to do with that minus 1? I'm going to distribute it. Right. So then I have now 2 minus 1 times 2 is 2 minus h all over 2 plus h times 2. That's nice. 2 minus 2 goes away, leaving just what in the top? Negative h over 2 plus h times 2. And there's not much I can do with that. I'm done there. That's as simple as it gets. So I changed it from a subtraction of 2 fractions to a single fraction. Next step, part 3. All right, so step 2 was to do the subtraction. Step 3 is going to be to do the division there. So new page. Step 3 is to figure out what is that difference over h. Okay, so let's see, what do we got? We have negative h over 2 plus h times 2. What's another way to divide by a number? By the reciprocal. So the reciprocal of h would be 1 over h. So I'm going to do that.
We didn't distribute the.
How come I didn't distribute down here?
Yeah.
My general rule is if a denominator is factored, leave it factored and just clean up the numerators. Because that tells me if anything in the numerator will cancel with the denominator. So that's a safe thing to do there. So here, ignore the negative for a minute. I'm multiplying by h, and then I'm dividing by h, all right?
Yes.
Yeah, so what happens to those h's? Oh, we're not quite done, Aaron. We'll be done with class in a minute. Oh, different class, sorry. Yeah, so h over h is 1. But what's stuck in the numerator? So I get negative 1 over 2 plus h times 2. And aside from distributing the 2, which we could do, I like to leave it undistributed if it's in the denominator. But in this case, it won't make much of a difference. So now I can do step 4 is to take the limit as h goes to 0. Well, we have limit rules that says we can take the limit inside the quotient as long as those limits exist. H is going to 0 here, so I think I have negative 1 over 2 times 2, or negative 1/4. I think that's the slope at that point on my graph. So I'm going to do a quick sketch and plug it into my computer. 30 seconds. So that curve looks something like this. Here's the point 2, 1/2, right there. Does it seem reasonable that the slope through that point is negative 1/4? That seems reasonable. And I could plug it into my graphing tool just to check. So quick check, clear, 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 enter your function. I'm going to get a new screen because that one is the wrong scale. F of x equals 1 over x. And I'm going to use tangent line, which point slope is the easiest way to go. Y minus 1/2 was the y value we found there, equals negative 1/4 times parentheses x minus 2. And yeah, that looks pretty darn tangent at the point 2, 1/2, doesn't it? Mm-hmm. Yeah, and we can zoom in there to get a better feel for that. And the cool thing about the graphing utility, it would tell me if there's more than one point there, meaning I have a secant by mistake. But it seems to only be finding a single point of intersection there. Right. I didn't have Desmos when I was taking Calc. Man, it's a little harder to do all this by hand. All right, we're out of time for fun with math. I would say we are 3/4 of the way through section 3.1. So we'll do a little more with 3-1 and start 3-2. And guess what? 3-2 is almost exactly the same as 3-1. There's not much difference.
So if you didn't understand 3-1 and 3-2.
You will understand 3-1 soon. Because you're going to do some homework this weekend, and we're going to go over it on Tuesday. Have a good day. Do good math.